Thank you very much, Ivan. It's my pleasure to have a chance to give a talk here. And I would like to thank organizers, especially Professor Malomed, for the invitation to come and give this presentation. So it will be a short summary of some relatively recent research results, chiefly theoretical, but also some experimental results will be demonstrated too. And the general idea is to realize physical possibilities for wave dynamics, which is governed by, roughly speaking, fractional diffraction or sometimes fractional dispersion. Okay, so as a mathematical curiosity, a possibility to introduce derivatives, ordinary derivatives of the fractional order were discussed long ago, in particular in this classical work of the famous Norwegian mathematician Niels Henrik Abel. And in terms of more abstract mathematics, a rather commonly adopted definition of the fractional derivative, it is the so-called Caputo derivative. Caputo is an Italian mathematician who developed it in the rigorous mathematical form. So the definition is relatively complex for the non-integer order of the derivative. It is written here. But this all was a part of abstract mathematics. Even, as I mentioned, it was considered as sort of a mathematical curiosity. In physics, the concept of fractional derivatives, which represent what may be called fractional diffraction, was introduced in the year 2000. It was introduced in the famous, currently is a theoretical work, which became very famous by a theoretical physicist from Canada, Nikolai Laskin. And what he tried to do, he actually derived the quantum mechanical Schrödinger equation, in which the kinetic energy operator is represented not by the traditional second derivative, but by a derivative of a fractional order. So to this end, what he did, he considered the quantization of the motion of a classical particle, which at the classical level performs stochastic motion, not in the form of the classical Brownian motion, but it performs stochastic motion by means of rapid jumps, or the so-called flights. So this specific regime of, roughly speaking, fast diffusion is usually called, this regime of the stochastic motion of the classical particle is called the regime of Levy flights. And if you can take some particle which moves randomly, stochastically in one dimension, and you will look how the absolute value of the distance of this particle from the center grows at large values of time. So the commonly known diffusion law, which corresponds to the Brownian regime of motion, it will be square root of time, which means that this coefficient alpha will be equal to 2. So this alpha is called the Levy index. And the regime of fast diffusion, which is performed by means of the Levy flights, it corresponds to alpha, which is smaller than 2. Then at large values of time, if alpha is smaller than 2, actually the mean distance traveled by the randomly moving particle will grow faster than in the classical regime. Now, Laskin proposed to consider the quantum, this particle in its quantum form, and he used well-known formalism of quantization, which is based on the Feynman's path integrals. So it means that actually, maybe let me move one step backward. Okay, yeah. So yes, it's okay. It is. Sorry. Okay. Laskin. No, I'm moving. Sorry, I'm moving to the wrong direction. Okay. Okay, so Laskin derived the equivalent, the specific form of the Schrödinger equation, first of all in one dimension. And he derives the Schrödinger equation by means of the mechanism which is called the Feynman path integral. So one should consider the manifold of all classical trajectories as trajectories of the stochastic motion which connect the initial and final point of a given trajectory and perform the integration of exponential of I times the classical action which corresponds to this arbitrarily chosen trajectory. So when he realized this formalism not for the traditional particles whose stochastic motion would be performed in the form of the Brownian stochastic motion, but when the particle at the classical level would move by means of the Levy flights, eventually Laskin derived the equation which is written here. So it is a normalized form, of course. It is a one-dimensional fractional Schrödinger equation. It includes the usual term with the external potential. Here there is no difference. But the kinetic energy operator is represented by this fractional derivative. And the question, of course, is exactly how this physically relevant fractional derivative, which represents the kinetic energy of such a particle moving by Levy flights, how it would be derived. It would not appear in the form of that cumbersome abstract definition of the fractional derivative elaborated in abstract mathematics by Caputa. Instead, the natural definition which appears in this fractional Schrödinger equation has a much more intuitive form. Namely, one can easily expect that if this is the operator which represents this fractional kinetic energy in the coordinate space, its image or its transform in the Fourier space would simply amount to the multiplication by absolute value of the wave number to this power alpha. And then the intuitively clear definition works as follows. Take this wave function psi as a space of coordinate, perform Fourier transform. In its Fourier form, multiply the wave function as a function of the wave number by this factor, and then return back to the coordinate space. So perform the inverse Fourier transform. So this, mathematically speaking, this, so to say, more intuitively clear definition of the fractional derivative was also developed by some mathematicians. In particular, it's called usually Riesz derivative. Riesz was a Hungarian mathematician who derived it in terms of more abstract mathematical setting some time ago. Okay, and so this is actually the operator of the fractional derivative, which naturally appears in terms of the fractional quantum mechanics as derived by Laskin. And actually, this is exactly what corresponds to the Riesz derivative in terms of the more mathematically rigorous treatment. So we see that actually this operator is not a differential operator. It's an integral operator, or sometimes it's called the pseudo-differential operator. Then also demonstrated by Laskin, one can similarly apply this to the two-dimensional situation. And then in the two-dimensional case, one will naturally derive the fractional Schrödinger equation in which the two-dimensional kinetic energy operator will be represented not by the usual form minus Laplacian, but this minus Laplacian to this power alpha over 2, which is explicitly given simply by the juxtaposition of these two natural definitions, which are based on the direct and inverse Fourier transform. Okay. Now, after this very short introduction, let me mention just some points which I will try, some particular results, which I will try to very briefly represent here. And the two probably most essential points in this list are, first of all, this will be the possibility to really emulate this fractional Schrödinger equation instead of quantum mechanics in terms of classical optics. And the second noteworthy result is the recently reported first experimental realization of this fractional regime, not of diffraction actually, of the group velocity dispersion in fiber optics, but quite similar to what may be expected here. Then some other points, in particular, I will maybe say a few words about some purely theoretical results for all kinds of fractional solitons when we also include nonlinearity in this type of the models. Okay, so thus far, this idea of fractional quantum mechanics has not been demonstrated experimentally, at least as far as I know. And then the next idea was proposed by Italian physicist Stefano Longhi more recently in 2015. And what Longhi suggested, he suggested to use a commonly known similarity between the quantum mechanical Schrödinger equation and the paraxial equation for the paraxial propagation of light in classical optics. So that mathematically speaking, these are two equivalent equations, as a matter of fact. In particular, so this means that actually paraxial propagation in classical optics in many cases can be used to emulate various setups known in quantum mechanics. And so the particular idea proposed by Longhi was to use this optical cavity. And the optical cavity considers the transmission of the beam of light. Now, the idea would be to implement this effective fractional diffraction with respect, sorry, I jumped back, which is not, I know, sorry, jumped in the wrong direction for the time being. Yes, okay. So the idea of Longhi was take this beam of light, and maybe it's possible to effectively implement the fractional diffraction concerning the transverse structure of this beam. So this will exactly correspond to what is called the paraxial diffraction, right? So his idea was pass it through the lens. The lens will, roughly speaking, perform the Fourier decomposition of this beam into its different components with different values of the transverse wave number k. Then so it will be essentially split into a set of a large number of parallel beams, each carrying a particular almost monochromatic value of this transverse wave number. Then this set of parallel beams should be passed through a specially devised phase mask. And the phase mask is devised in such a way that each particular component which carries a particular value of the wave number will pass through this phase mask at some particular distance from the center, and it will thus be given a particular phase shift. And then the structure of this phase plate should be designed in such a way that actually the distribution of these phase shifts for different spectral components will exactly emulate what you expect from the formal action of the fractional diffraction. So roughly speaking, for the wave number k, the phase shift induced by this plate will depend according to this simple expression. Then the second lens is used to recombine all these separated beams into a single one, which will keep propagating in the system. Of course, by means of this procedure, one will not actually implement continuous evolution described by the fractional Schrödinger equation. One will only perform the one-off map. But now the next idea was to consider the circulation of light in this cavity so that each particular passage produces a small effect, and then one should average these effects with respect to the large number of circulations, and eventually in this approximation, as was demonstrated by Longhi, one will indeed rederive effectively the diffractional form of the Schrödinger equation. Similarly, one can emulate the two-dimensional version of the fractional Schrödinger equation simply if one will consider this two transverse coordinates in this geometry. And then there is some illustration. The traditional potential, for example, the harmonic oscillator trapping, can be also realized in terms of this optical scheme by means of some additional optical element. This is some additional mirror inserted here, as was demonstrated, can emulate the effect of the harmonic oscillator trapping potential. And as an illustration, one can numerically solve this, find the eigenstates, eigenmodes of this fractional linear Schrödinger equation with the harmonic oscillator potential in one dimension. And just this is the illustration. This will be in particular when the Levy index is equal to 1. 1 means this is, roughly speaking, square root of the traditional operator of the kinetic energy, because traditional operator corresponds to alpha equal to 2. So this is a numerically found, as an illustration, a numerically found ground state wave function. And these are some examples of excited states trapped in the harmonic potential. Okay, next, still this proposal of creation of the fractional diffraction was not experimentally realized either, as far as I know thus far. But what was recently done, a similar idea was realized not in terms of the fractional diffraction, but in terms of the fractional group velocity dispersion in fiber optics. So not in the spatial domain, but in the temporal domain. Okay, so this was done in this experimental work relatively recently. And the idea was, roughly speaking, similar. So one considers the pulse of light, which propagates as optical fiber. Now one passes it through the lens, which decomposes it into spectral components, nearly monochromatic components, with almost each one carrying almost a constant value of the optical frequency. And they are, for the time being, they are spatially separated into a set of parallel beams. Then each beam passes a specially devised, face plate. Actually, this face plate was created as a computer-generated hologram. And then each spectral component will be given a particular phase shift, which emulates what you expect from the action of the fractional time group velocity dispersion. Then another lens is used to recombine all the spectral components into a single optical pulse, which propagates in the fiber. So this possibility was realized experimentally. And in terms of the theoretical description, it's the equation which can be used to describe it is written here. It's actually, this part is just the traditional linear Schrödinger equation for the light propagation with various orders of the traditional group velocity dispersion, starting from the second order dispersion. And this separately written is term with the effective fractional group velocity dispersion. This term should be taken into regard also because in the real experimental situation, one cannot realize only the fractional dispersion. The traditional dispersion also is acting in the system and should be taken into account. Okay, and then these are some results. So in the top row, what is shown are the numerically simulated results, and these are experimentally observed counterparts. So this alpha is the Levy index, which characterizes the fractionality. So traditional diffraction, which corresponds to alpha equal to 2, when this is just the traditional diffraction, it's very strong and it immediately simply destroys the input. Nothing happens. Now, if we try to realize a fractional dispersion in competition with some traditional dispersion, in this case, so L is actually the effective parameter which characterizes the length of the traditional dispersion, which acts in competition with the fractional dispersion. So here, two dispersions are in competition. because the fractional term has anomalous sign, while the traditional term has the sign of the normal group velocity dispersion. So they keep balance in the course of some propagation, but then finally this fractional term becomes dominant, and it leads to the splitting of the temporal signal. On the other hand, if one will take the negative sign of this coefficient, which means that now both the traditional dispersion and the fractional dispersion have the sign which corresponds to the anomalous group velocity dispersion, they will act together and they will very quickly split the input into two. And then there are some intermediate possibilities when they compete. Okay, and now coming back to the theory, if one is going to implement the fractional dispersion or diffraction in terms of optics, in optics, of course, it may be quite natural to take into regard the fundamental material nonlinearity of this optical material, such as, first of all, the Kerr self-focusing, of course. And then in many theoretical papers, people consider the model of this type. Sorry, too early to jump here. People consider the model of this type. So this is a one-dimensional fractional Schrödinger equation with some potential. And this time, what is added is a traditional Kerr effect, so self-focusing of light. Then analysis of this one-dimensional equation demonstrates that it has some special properties, namely, if this coefficient alpha, the Levy index, takes value between 2 is the classical value, and up to 1, in this interval, one should expect the existence of stable solitons. However, if alpha is exactly equal to 1, then one can easily predict that this model gives rise to what is called the critical collapse, so catastrophic self-compression of light. And if alpha is smaller than 1, then this will be a supercritical collapse. So to say, it will be a real disaster which would happen to the optical signal. And similarly, one can analyze a two-dimensional version of the fractional nonlinear Schrödinger equation. In that case, actually, the situation is still more challenging because now it's easy to see that the supercritical collapse will take place for all values of alpha smaller than 2. Okay, and one more possibility not related to optics. Coming back to the fractional quantum mechanics as introduced by Laskin, one can think, what about the possibility to consider an ultra-cold gas of particles which move according to the fractional quantum mechanics, and maybe they can form a Bose-Einstein condensate. And then maybe one can derive the Gross-Petaevsky equation for this condensate as the direct counterpart of the nonlinear Schrödinger equation. And then one can try to predict some matter wave patterns, like, for example, matter wave solitons, vortices, and so on, in terms of this presumably existing fractional Gross-Petaevsky equation. Thus far, it was not, this derivation was not performed rigorously, but at least some theoretical results were published based on the assumption that maybe this fractional Gross-Petaevsky equation may be used. Okay, now there are some reviews about chiefly theoretical results concerning chiefly roughly speaking, the topic of the fractional solitons and fractional vortices. So when the nonlinearity is taken into regard, this is a relatively old review, and this is a more recent review. Okay, and now the first example of the nonlinear effect, which may be predicted, these are domain walls. So one can consider the propagation of light with two orthogonal polarizations or two different carrier wavelengths. In that case, as is well known, it will be governed by a system of two coupled nonlinear Schrödinger equations. Now we consider the signs, we consider the signs which correspond to the self-defocusing interaction of light. So the bright solitons are not going to appear, but we can expect, but if this coefficient beta of the cross-phase modulation is larger than 1, we should expect that it will be essentially the immiscible binary fluid of light where two components would like to separate. And now one can analyze how this, so then because they separate, they form a boundary between two different areas, which is called the domain wall. And the question is how the main wall will look like in the case of the fractional diffraction. So this analysis is relatively simple. And so this is set of results. For example, this is a set of solutions for the stable domains walls, which are obtained when we fix all parameters except for this fractionality parameter, the Levy index, and it may take all values from very small, such as 0.1, up to 2.0. This means the traditional diffraction. Okay, so these domain walls really exist. Now, what is maybe more interesting, this is an attempt to predict some matter wave patterns. If, as I said, it's still only a conjecture, if one can postulate the availability of the fractional Gross-Petoevsky equation, this time for the two-component Bose-Einstein condensate, and one can consider a specific coupling between the two components in the form of the spin-orbit coupling. Recently, this physical mechanism has drawn a great deal of interest in studies of Bose-Einstein condensates. Okay, so in that case, what we will consider, the two-component system of two coupled Gross-Petoevsky equations. Now, what we see in these equations, we see this is the presumed fractional kinetic energy operator according to the theory of Laskin, and all other terms are usual. So this is the nonlinear self-interaction. This time, this common sign minus implies we consider self-attraction, both self-attraction and also cross-attraction between the two components. And this combination of linear terms, linear coupling terms, this is exactly what represents in the standard form of the spin-orbit coupling. So these are terms which perform linear mixing between the two wave function, two components of the wave functions phi plus and phi minus, but the linear mixing is performed not directly. It's performed in terms of the first derivatives, first special derivatives, and all the system is two-dimensional by definition. Okay, then this is okay. Then one can, of course, one can try first of all to look for stationary states with some chemical potential mu, obviously, and then one can consider this possibility to what was done some time ago, 10 years ago, actually, for the traditional system of Gross-Petoevsky equations with a spin-orbit coupling. In that case, this, by the way, somehow establishes the link between all this activity and, on the other hand, the theme of chirality and the topology and all that, because in the two-dimensional case, a natural object which is created by this system is the so-called semi-vortex. So semi-vortex has a natural structure in two components, which is written here. One component is simply zero vorticity one, and the second component, coupled to it linearly by the spin-orbit coupling, it is the component which automatically carries vorticity plus one. So this combination of two vorticities and two components, 0 in one and plus one in the other, or alternatively minus one here and 0 in this component, this is the combination of vorticities which are naturally admitted and promoted actually by the spin-orbit coupling. So this analysis was done previously for the traditional diffraction, which corresponds to the traditional quantum mechanics, traditional Gross-Petoevsky equations, and it was found that such semi-vortices, solitons with these two structures, with this structure, they are stable. Why this is a non-trivial result that they are stable? So this is a typical example, cross-section of such a semi-vortex. This is a cross-section of the zero vorticity component, and this is a cross-section of the absolute value of the component with vorticity 1. And this is a family of such semi-vortex solitons, which is described by the dependence between chemical potential and the total norms, roughly speaking, the total number of atoms in this matter wave soliton. Now, what is remarkable here, in the two-dimensional system of nonlinear Schrödinger equations with the cubic self-attraction, a commonly known fact is that the critical collapse takes place. Therefore, before this work, it was believed commonly that formally one can construct, of course, two-dimensional solitons, but they will be always unstable because of the presence of the collapse. And now the non-trivial result is that the spin-orbit coupling stabilizes them and makes such semi-vortex objects stable against the collapse. And then This was now extended to the case of the fractional Gross-Petayevsky equations, and now the result is still more remarkable because, as I mentioned, in this case, for all values of the Levy index smaller than 2, one should expect supercritical collapse, so terribly strong instability. Nevertheless, if the norm of the semi-vortex takes place smaller than this critical value, and this is this analytical prediction by means of the variational approximation, in that case, still, we have a family of stable semi-vortex solitons supported by the fractional kinetic energy. Okay, so these are examples of such stable solitons for different values of the Levy index. They are shown by their cross sections. Okay, now, how many minutes do I have? Okay, now, okay, I will just mention two other things without going into detail, which were fractional solitons were also predicted. This is a one-dimensional model in optics in terms of the second harmonic generation. It's a system of two equations for the fundamental and second harmonics. And here actually the diffraction is taken in the fractional form. And here it was possible to find again the family of stable solitons, which is briefly speaking, it's a paper where it was done. It was so these are just examples of such stable solitons, second harmonic generation solitons produced by the system of equations with the fractional diffraction. And finally, let me just say a couple of words. This is already the conclusion. The conclusion is that the idea of fractional derivatives was introduced long ago as a mathematical curiosity. Then in physics, it appeared in the form of fractional operator of the kinetic energy in the new type of the Schrödinger equation, which was introduced by Laskin 24 years ago. Because of the difficulty of the experimental realization of the fractional quantum mechanics, it was proposed by Longi to emulate it in terms of the paraxial propagation of light in optics. Thus far, it was not realized easily experimentally, but quite recently, a counterpart of this idea was realized experimentally when it was demonstrated that one can create effectively, instead of the fractional diffraction of light, one can experimentally create the fractional group velocity dispersion of light. Okay, so there remains, of course, many problems for the development. In particular, very few results were obtained experimentally, and for example, as I mentioned, the possibility of the fractional diffraction in optics thus far, as I understand, has not been realized experimentally. Okay, that's all. And just the last word is that there is a journal which may be well interesting for some people who are interested in all these topics. In particular, in this journal, we are now putting together a special issue on the combined topic of symmetry and simulations of nonlinear wave dynamics. So maybe some people would be interested to submit contributions to this special issue. Okay, thank you very much for your interest.
Thank you. Do we have questions?